Okay, am I here? Am I... Where are you guys? Hello? Hi. Yes. I am here. Good morning, everyone. Good morning. I've had technical issues. Uh, I'm sorry. Can you guys hear me? Where are we? Yes. Okay. Can you guys hear me well? Audio. I've had a lot of audio problems today. All right. Ooh, I see so many familiar faces. Hello, everyone. Um, Thanks for joining. Okay, wonderful. I thought we were not gonna make it, but we made it. I had microphone problems. I don't know what was going on. I literally had to restart and start over again. But we're good now. So we should be ready to go. I am so excited about what we're gonna do today because it's one of my favorite topics in the world. You know that. So okay, so what I have some messages here. Uh, okay, I see a lot of familiar people. Wojtek, Vava, how you doing? Arquitectura paramétrica as well. Chandra, Professor, Cities of the Future, Rami. Welcome everyone, and thanks for joining. So, I'm sorry. I'm sorry we started a little late today. We usually start at 10 a.m. But I had to. I was actually on a. I was actually on a review by a colleague of mine and a friend of mine from the GSD, Hyojin Kwon. I was on her final review for the course pre and post, which I have to say the student work was so cool. It's an exploration on concepts of classic architecture, but looked through the lens of new digital media and image manipulation techniques and architecture and form generation techniques. I thought it was extremely cool. I'm going to paste here the link on the chat so that you guys can check the main landing page and the student work. I think it's really cool, especially if you're into architecture. I thought it was like extremely interesting exploration. Speaking also of final projects, I want to share some progress. So many of you know that this semester I was teaching a seminar here at Harvard at the Graduate School of Design called Enactive Design: Creative Applications Through Concurrent Human-Machine Interaction. I was co-teaching this seminar with my friend Zach Siebold, and the course was an exploration on how can we as humans in collaboration with machine agents. So, for example, robots, 3D printers, neural networks, other machine learning frameworks, I don't know, but like with like devices that have some kind of agency and autonomy, how can we, through that conversation and that collaboration in real time, how can we open up new creative space? And and I have to say, we had the final review last Wednesday, and it was incredible. I'm super proud of my students, especially given the circumstances, given how bumpy the semester was about all these changes and like losing access to all the robots and all the machines that we had. And I would like to. I'm gonna paste here the link to the semester to the course if you guys want to check the syllabus. And I also want to share the playlist that we've done with the student work. This is not so much shameless promotion, but it's more about like I really want to bring this work out to the world and have and share it with people so that folks like you who are interested in computational design and what creative opportunities we can find through code, through robotics, through machine learning, what kind of things we can make and we can explore, right? Um, so yeah. So if you guys want to check it out, this is what we did this semester. I want to give, well, first of all, quick reminder. I want to remind everyone that we are moving, that we've talked about this before in previous streams. We're going to be moving the live stream from my personal YouTube channel, which is where we are right now. We're going to be moving to its own channel, which is going to be called Parametric Camp. Is called Parametric Camp. So I would like to invite you, so that you don't miss out. I would like to invite you to subscribe. I already pasted the link here on the YouTube chat. And we will be transitioning slowly into that channel, so that at some point we're only going to be streaming from there. So as you already know, already the videos that we're producing, the edited videos, we're only posting them there. And we will be transitioning between streaming here in this channel and streaming in the other channel over the course of the next few weeks. So today is going to be the first day of such transition, because I'm going to do a stream. I'm going to do a stream where I'm going to do 2 geometry gems, and I will explain what I'm going to do in a second. I will do the first one here this morning in this stream that you guys are at. But then the second part of that stream, it will be the first time that we will be streaming from the other channel, from Parametric Camp. So I would like to invite you. I'm going to paste here on the chat, I'm going to paste the link to the stream that we will do this afternoon, which will start at 3 p.m. Boston time. Okay, so the first part of this video, I will do it here. The second part of this video, of this tutorial, I will do it already in the Parametric Camp channel. Okay, so please feel free to subscribe to the other channel, to like set yourself a reminder for this afternoon's. I'm splitting it in two because I was late to this stream today. But also I have meetings in the afternoon, so I can only start again after 3 p.m. my time. Okay. So, okay, and I want to give a shout out to somebody who's. Oh, I think I saw her before in the chat. I think Vava from India. Are you there? Can you say hi to us? And I want to give a shout out because the other day, you know how we've done 2 streams on Grasshopper Sharp on this project. Yeah, there she is. You know how we've done 2 streams on. You know how we've done 2 streams on Grasshopper Sharp, which was this idea of like, let's take vanilla Grasshopper components and let's try to mimic the exact same functionality with C#, so that we can learn those transitions of how things are implemented natively, and therefore we can improve our low-level computational design skills and geometry generation skills. So I think I mentioned during the stream, like, hey, if you guys wanna try it out yourself, if you want to like tinker or maybe, and then she messaged me and she volunteered to give it a try, and she sent me this file, which is basically the full vector point tab, so all of these components, but reconstructed here in C# components. And I'm also extremely happy from her work, because she did a really good job at adding a lot of comments and writing code that is very clean to read and very clean to understand. Look at this. This is wonderful. So I'm giving you huge thumbs up and shows of gratitude. This is going to definitely make it to the repo. So thanks for that. And let's keep making this awesome. Thanks a lot, Baba. All right. And so, and where was I? Okay, so what are we going to do today? Today, oh yes, what are we going to do today? Today we are going to build a geometry gem, which is going to be a polyline simplification algorithm. Okay, what does that mean? Very often you have a polyline, and the polyline has like maybe 100, 1,000, 10,000 points, but maybe that polyline is got too much of a density of points in that polyline, and what you want to do is you want to simplify it so that it keeps the original spirit and like the original shape, but with many less points. This is very useful, for example, when you're creating applications where you're drawing on the screen and like there's a lot of points that redundantly draw on top of each other very close. So that's very useful. For robotics, for example, when you create a trace, you don't really want to go through like a million points. You just want to go through the ones that are like very important to keep the essence of the shape. So this is a very common thing to do, and it's not very hard to implement. So I would like to spend some time today doing a polyline simplification algorithm, and for that I'm going to choose the Douglas, yes. For that, we're going to implement today I don't know how to pronounce this, the Raymer-Douglas-Peucker algorithm for polyline simplification. If you see on this animation, what we have here is a polyline that gets simplified over certain steps. So we're going to implement this, but before we do this, we're going to need, and I will explain why in the algorithm. We will need to have another geometry gem, which is going to be the possibility of computing the distance between one point. Okay, so I'm not. Yes, so here. All right, sorry. I was not there. Yes, going back, we're going to implement today the Raymer-Douglas-Peucker algorithm for polyline simplification. And if you see here from this diagram, what we have is a polyline that has a lot of vertices, a lot of points. And in an iterative process, we're going to start removing the ones that are not really contributing much to the overall shape. And we're going to keep the ones that are significant to be faithful to the original shape, even if more on a lower resolution way, you know? So as you can see, for example, this vertex, and they're not really contributing much to the overall shape. But this one, and this one, they are very important. So what we're going to do today is we're going to implement this. But in order to get this going, we need to be able to do something that we can't do yet, which is going to be computing the perpendicular distance from one point to a straight segment, which is a super interesting problem in itself. It's very simple to solve, but it involves a little bit of vector algebra, which you already know is my favorite topic in the whole world. So what I thought of doing was, this morning we're going to implement a geometry gem, which is going to be calculating the perpendicular distance between a point and the line. And I'm going to show two methods on how to do that, and I will explain where they're coming from. And then once we have that in our toolkit, then this afternoon we will implement the polyline simplification algorithm using this other geometry gem that we have developed this morning. Okay? And these two gems will be part of this series that I want to start, which is like which I'm calling geometry gems, which is like, let's write down algorithms to do cool geometry manipulation or cool geometry analysis. All right? How is that sounding? Oh, I see a lot of activity in the chat. All right. Are you guys excited? I am so excited about this. Oh my God. Okay. All right. So where are we going to start? Yes. So okay. So let's do the following. And as usual, what I'm going to do is today's live stream is going to be, we're going to implement these two gems that I described, and then by the end of the second one in the afternoon, I will spend some time doing Q&A. Okay? So again, if you guys want to join for this afternoon's meeting, this afternoon live stream, I'm pasting the link here on the chat, and you can toggle the reminder, you can whatever. Okay? All right, so shall we get started? I think we shall get started. Yes. So, okay, so how are we going to start? That's always a good question. So, I think what we're going to do as usual. I'm going to start putting this together, and then I will record the introduction by the very end. I would like to replicate what we want to do in native Grasshopper first, so that we have like a way of validating our values, and then we can compare them with the original. So I'm going to I'm going to write here, I'm going to add, how do you turn on seaplanes? How do you, do you guys remember how to turn off visualizing the seaplane, like the grid lines? What was the shortcut, or what was the command? I'll wait for you. I just don't want to see the grid line on my screen. So I'm going to add 2 points, and then I'm going to add another point here. And then I'm going to grid, wash deck, choose grid property. Oh, okay, interesting. So apply show world axis. I don't want to see world axis. No, wait. I want to see. Nope. What have I done? Show grid axis. Show grid. Okay, that's what I want. All right. Yeah, so I want this, but I don't want the main one. Okay, and then, oh, F7? Oh, okay, I like that one. Okay, so if I turn this off. All right, you guys are really good at this. Thank you. Yes, I like F7. So if I do this, boom. Oh, great. That sounds great. Okay, so I'm going to move this. Nope, I'm going to move this somewhere here. And I'm going to, okay. And then I'm going to bring the points. I'm going to bring in here 3 points. This is going to be 1 here. This is going to be another one here. And this is going to be another one here. Okay. And then I'm going to make a line between the two here. I'm going to compute, for example, here. I'm going to closest. How can I project this to the curve? Curve closest point, and then I have a point here, and I have a closest point. Let me do bifocals so that you guys can see this. Okay, and then I have the closest point. Nope, this is this point, this is this point, and this. I want this point to be here. Yes, so I want this one. Okay, and then this gives me the distance here. So that's going to be what I want, the value of 7 point whatever. Okay. All right. So this is what I'm going to use to verify that this is working. And why not use this? Just simply use this. Well, because there's like, if you use vector algebra, this component is doing it for any nerves curves. But if you use vector algebra, you can find a more optimized way of doing this for a straight line. So that's what we're going to do today. So something like this, for example. So we're going to, maybe this is a good point to start the video. If we start here, I can start talking about, so this is what we want to do. We want to calculate this distance, and then I'm going to write a C# component that takes the 3 points and then gives me that, and then I will have to jump into whiteboard. I'm going to do a lot of whiteboard today, so because I want to really explain the concept. So let's do that. Okay, so so that's B. This is going to be P. This is going to be A. This is going to be B. Okay, this is going to be what we're going to compare against, and this is going to be inputs, and then I will do the rest here on. On video mode. Great, so let's first start with the basics. What I've done here already is I have created a simple grasshopper definition that takes 3 points that are coming in from Rhino. So this point here, the point that we want to calculate the distance to the line, and then 2 points that are going to define the line that we want to use for calculations. So I've created like a very simple vanilla definition where I'm creating a line between those 2 points, and then I'm finding which one is the closest point to this one on the line, which is also the one that ends up being perpendicular to this line. And this component gives me the point, it gives me the parameter, but it also gives me the distance between the projected point and the point on the line, which is the value that I want to calculate with this geometry gem. Okay, so I'm doing this just for the sake of verification to know that my values are correct. So I have created a C# script component here that takes P, the point that I want to verify, and then A and B, the 2 points that form the line that I'm going to be projecting on. So I'm going to plug those 2 in here, and as usual, you have to remember to right-click on the input and specify the correct type. So these are going to be point 3D, each one of them point 3D and point 3D. And then here I'm going to plug in a panel to make sure that we understand that we get the output. And with this, I'm probably ready to start coding. But as usual, and this is super important, I want to always invite you to take some time to think about what you're doing before getting into the code. So what I would like to do is I would like to spend some time diagramming and explaining what the algorithm that we're going to implement, how it works and where is that coming from, and to understand a little bit of the vector algebra that is behind what we're going to just do right now. So let's go into the whiteboard and let's break this problem down. Awesome. So whiteboard. Okay, there's going to be a lot of this today, so I'm going to ask you for patience because yeah, it's going to be it's going to be a lot. So how are we going to do this? So we have 3 points, and so I'm going to do black, and I'm going to do 1 point here, another point here, and P. And can I write text on this thing? Do we like say go it? This what is this? P. Well, this is not. I don't like this. Wait. So now P. Oh, so I get like okay. Okay, this is going to be A, for example. What is this? I have no idea what's going on here. Oh. Okay. Yeah, A, and then another one is going to be B. I need to take a look at this. Nope. I want to move this. Exactly. This is really weird interface. Okay. So we have this diagram, and okay, and I'm going to draw a. No. Oh my God. I need to learn a little bit more of this sketch drawing, whatever this is. Okay, this. Okay, and then another layer, and I'm going to draw like a really faint line between here and here. Okay. All right, that looks terrible. But I guess it is what it is. We can't do much better these days. I need to get like an iPad or something here that I can draw with. Okay. All right, so I think we're ready to talk about this problem. How am I going to do this? I'm going to explain that this is basically 2 vectors, and that we can use the dot product to figure out this problem. Okay, so I'm going to do that. Yeah, it's just really hard to draw the letters on top. So if I do A, P, and B, is that any better? If I draw, all right, is this any better if I do A, P, and B? Is that any better? What do you guys think? I don't know. And also, what about straight lines? Can I draw straight lines? Is there any way to draw straight lines here? Okay. With the ruler. But then, what is this? Why can I not just like, this is I need to find a better drawing program, maybe? I don't know. Anyway, well, let's just, what am I, I'm going to, I don't like this. I'm going to, how can I delete this layer? Okay, I don't even know how to do that. Okay, I'm just going to keep the letters like this, okay? All right, so let's start. I'm going to, okay. And then I'm going to draw here. I'm going to draw on a new layer. I'm going to draw this, and I'm going to draw H. This is what we want to find. Okay. Okay, so let's do this. So you can see here on the screen, I've drawn like the worst sketch ever to depict the idea of what we want to do. But the idea is basically this. We have a point P, and we want to find the distance h of that point P to a line that is formed between point A and point B. And it just so happens that the closest distance to that line also happens to be the one that is perpendicular to this line. So the line H is perpendicular to A and B. So why is this important? It is important because it helps us break down the problem through some trigonometry, and it also helps us because we can apply some of the interesting rules of vector algebra in order to figure out this problem. We have started this problem by talking about 3 points, but actually what I would like you to understand is that these 3 points, are just 3 points floating in space. They don't have any known relation between them, but we're actually going to assimilate these 3 points to 2 vectors, and using those 2 vectors we will be able to operate and find the distance h that we're trying to find here. And those vectors are going to be, first is going to be vector AB, a vector between point A and point B, so this point here, a vector that is basically representing the line that that is formed between point A and B, and then another vector that is going to be between the starting point of the line and point P. Actually, it wouldn't matter if we used the vector between B and P. It doesn't really matter, but we're going to operate between those 2 vectors so that we can find the length of the distance between P and this particular vector between A and B. How are we going to do this again? I'm losing it a little bit. So we're going to do that, and I'm going to explain now that this is a triangle, and that the triangle, we can do trigonometry in this triangle, and therefore, yes, okay. Okay, so let me draw another diagram here. Where are we? Where am I? Here. Can I not move this? Can I not move this layer? Okay. All right. Okay. So I'm going to do black. All right. Let's do it. Today, in this stream, I'm going to show you how to calculate that distance in two different ways. And the first one is going to be using the properties of the dot product of two vectors. Why are we doing this? Because if you think of these two vectors in three-dimensional space, you can see that because h is the length, is the segment that joins P and the vector A and B in a perpendicular way, it just so turns out that we can think of this problem as a trigonometry problem where we have a square triangle here. This here is going to be the length of the vector AP, so it's going to be how long this vector is. This h here is going to be the distance that we're trying to find, which we don't know. And then L is going to be this distance here between the beginning of the vector. This vector ends whatever, it doesn't matter. But L is going to be the distance between the starting point of the vector and where the segment H hits this vector. This is what is usually referred to as the projection. If we thought of this as a vector here, we could think of this as the projection of the vector AP on top of the projector of the vector AB. So this could be the projection of AP over the vector AB. So this is A, this is P, and this is B. And the angle that these two vectors form is called theta. We're going to call it theta, for example. What's interesting about this is that we can find trigonometry relationships between this this triangle. We will do that for the other way of calculating. But for here, the first one we're going to do is we're going to use the properties of the dot product. And if you remember, I may link to a video somewhere here that describes that. If you remember, the length of this projection, so the length of this vector, and I'm going to write it here, the length of this vector is equal to the, it's going to be equal to, sorry, I'm going to rewind back. That did not come out well. So if you remember, the basic rules of trigonometry say that the cosine of this angle theta is going to be equal to L, so that length of the projected vector that we don't really know yet, divided by this other side, the length of the vector AP, which we do know because we do know all those points. If we reshuffle this a little bit, we can see that L is going to be equal to the length of the vector AP times the cosine of theta. Okay? Now, where things get interesting is that we can manipulate this a little bit more and say, well, if this is true, then I can take this part and I can multiply both the numerator and the denominator by the same value. So I'm going to say, I'm going to create a fraction here, and I'm going to say AP, the length of AP, times the cosine of theta times this new factor that I'm going to introduce, which is going to be the length of AB. Okay? And I'm going to also divide everything by the length of the vector AB. Why am I doing this? If I take something and I multiply it and I divide it by the same number, the value stays the same. Okay? So this that I just did here is exactly the same as this that I just did here. But why am I doing this? Because if you remember from vector algebra, and I will point to some documentation here on the videos, this that I have here, this part, equals the dot product of two vectors. So if you remember, if I have vector U and I have vector V, the dot product of those two vectors equals the length of one, the length of U, times the length of V, times the cosine of the angle that they both form. Is one of the properties of the dot product. So what is interesting about this? what's interesting is that now this length here is going to be equal to the dot product of U times V divided by, oh sorry, it's going to be equal to the length of AP times the length of AB. No, sorry, I'm messing it up again. It's going to be equal to the vector AP dot product, the vector AV, divided by the length of the vector AB. Okay? And if we push this a bit more, if the length of the vector AB happens to be 1, if we unitize that vector, then this is equal to the vector AP dot product, and I'm going to put a hat here. The hat means that this vector has been unitized, okay? So this is AB, the unitized version of AB. Oh, right, so this equals the length of that projection here. Okay, so let me write that somewhere. Let me write that somewhere here. So I'm going to say L equals AP times unit AB, for example. And I'm going to write that here. Okay, so can I, no, okay, so I have, okay, and then now I'm going to just erase all of this stuff here. Then I'm going to erase. Can I erase? Oh, okay. Oh, this is gonna take forever. Can I erase bigger? Can I? How do I make this bigger? Really, I need to sit down and like learn how to use this thing. This is like when you have to clean a real whiteboard. It just sucks. Hard eraser. Okay, there you go. Okay, let me delete all of this here. Okay, and we were here in ballpen mode. Okay. So let's get back, and now what I want to do is I want to do some trigonometry with this, just like the Pythagoras theorem, which is going to be super easy. Oh, okay, so it's taking me some time. Okay. Great, so as we just saw, I just wrote it a bit cleaner all the way up here. So we can, through vector algebra, we know that the length of the projection of the vector AP over the vector AB equals the dot product of the vector AP times the vector AB unitized, okay? The unit vector AB. But why is this important? It is important because now if we know the length of the vector AP, because it's just a given, and if we know the length of L, then we have a square triangle in space that we can apply the Pythagoras theorem to. I never know how to pronounce Pythagoras in English, but very simply, we can say that the hypotenuse, so the length of AP squared, equals the height squared plus that length that we just calculated square. Okay, and then the problem is just, I'm going to touch here, and then the problem is just as simple as we know this, we know the L, and then the problem is just as simple as figuring out H. So we can do here, we can do H is going to be equal to the square root of the length of AP squared minus L squared, which happens to be, as we just said, the square root of the length of the vector AP squared minus the dot product of the vector AP times the vector AB unitized, okay? and this is squared. So this very simple calculation is going to give us then the length of h, which is that distance that we wanted to find between P and the straight line formed between the points A and B. Let me write this in a clearer way, and I'm going to write it here, and then we get back to actually writing this in code form. Okay, so that means that h is going to be equal to the square root of AP squared. Oh, this is terrible. Minus AP minus IP times unit AB. Okay, and this is it, and this is it. Is that correct? Square root of this. Okay, so this, no! So, oh, I drew on the same, I drew again on the same thing. Oh my god, I'm the worst. Okay, so here. Oh, and no, and this is squared. I have to square that. How do I edit text? How do I change text? Edit text layer. Okay. So, no, not this one, this one. And this has to be squared. Okay. Okay. Okay, and then I'm just going to remove this. Yes. Okay, use brackets, Kartik, pixel car. Use bracket for what? Okay. So I think we're ready to. I mean, it's going to take so much long. It just took so much longer to explain that to actually implement. It's going to be like 3 lines of code. You guys are going to see. Okay. Use a book edge, IRL. Okay. Hey, Merit, how you doing? Good to see you. Okay. Yes, so this is it. I just cleaned up a little bit, but remember what we just discussed. The distance h is going to be equal to the square root of the length of the vector AP squared minus the dot product of the vector AP times the unit vector AB, all of that square as well. As you can see, it took quite some time to break this down, but I really like breaking down these like small trigonometry problems, because now you can see that you now understand where this expression came from, and you will see how implementing that in C# is going to be a piece of cake. So let's go ahead and do that. So I'm going to go back here to my script, and then I'm going to take here, I'm going to open my script, and I'm going to say, well, I'm going to write, first of all, according to the algorithm, what I want to do is I want to create the two vectors AB and AP. Okay, so AB is going to be the vector formed by subtracting the coordinates of point B minus the coordinates of point A. And then the vector AP is going to be the same thing, subtracting the coordinates of point P from the coordinates of point A. Is that working? Yes, it's working. And something that we may want to do is going to be, well, let's first calculate the value of L. So if you remember, let's first calculate the value of L, which I'm going to name the cross product, because this is going to be equal to the cross product of two vectors. One is going to be AP, and then is going to be the unitized version of AB. Let me do that as well. I want to say AB dot unitize, or we could do this manually, but we're just going to use Rhino Commons methods for that. But unitizing a vector is just as simple as dividing that vector by the length of that vector, just so that you guys remember. And then the cross product of these two are going to be AB times, which is already unitized, so AP times AB, which is already unitized. This cross product is going to be the length of the projection of AP over AB. Okay, and now going back to the only thing that we need to do to calculate the height is going to be the square root of these values. So I'm going to write here, I'm going to write double H is going to be math dot square root of what? It's going to be the length of AP, and we may want to calculate that as well. Length of AP is going to be equal to AP dot length. Okay, and then here we just say the square of that. So length AP times length AP minus the cross product, the square of the cross product. Is that correct? So you see here the square root of the length of AP squared, so AP times AP, and then minus the cross product of AP times the unit vector AB squared. So as we just saw, this is cross, and then let's see if that works. I'm going to output there, and boom, it works. We have the, we can move these points around, and then we have the straight distance between point P and the line form between vectors, between the 2 points A and B. Okay, and we did that with very simple vector algebra, only doing some trigonometry and understanding the relationships between those two vectors and their square triangle in space, and also with a little bit of the aid of the dot product properties. Okay, so let me take a little bit of time to take this code that we just wrote, and instead of having it as part of the main code, just write a very clean function that takes these three vectors, these 3 points, and then gives you the result. Okay, let me rewrite this in a second. All right, that's going to be as easy as just creating a double function that says distance to line, and I'm going to do here dot product, and this is going to be point 3D P, point 3D A, point 3D B. It's going to take all of this, and then it's just going to, I'm just going to copy paste this here, and then it's going to return the value of H. And then here we can say D is going to be equal to A and B. Okay, is this working? Yes, it's still working. Voila! So we have it here. So you can see that now my code is a little cleaner. I have packed this functionality that I just created into a function called distance to line, and I wrote dot product just because I'm going to do a different version of this. So I want to make sure that I know which version I'm using. This function takes 3 points, P, A, and B, and then returns the distance between that straight projection of P over the line of AB. And then I can just use this function now to calculate this. And the nice thing about this is that this function now is a self-contained function. So I could just copy paste this between this implementation that I wrote here in C# in Grasshopper, and then with very minimal changes, I could just implement this in like a pure C#, in like a pure C# script, in like a pure C# program, a library, other environments that use C#, like Unity, like VVVVV, like you know, all those things. So I think this is great. So I'm going to keep this here, and then what I'm going to do now is we're going to move to using a slightly different approach to calculating the same distance. But instead of the dot product, we're going to use now the cross product, which is definitely my favorite. Okay, so let's do that. Okay, but before we do that, I'm going to drink a little bit of water because I've been talking a lot. How is this going? You guys like this? I love vector algebra. That's why they call me Dr. Vector. All right. Whew. Okay. How are we going to do this? How are we going to do this? We are going to draw another diagram. We're actually going to, can we duplicate layers on this thing? All right, so can I merge? Sorry, I'm going to merge with below. So now we have these two are the same. And what about this one? Oh, this one I don't like. So how do you delete a layer? Delete layer. This one, oh, I also want to merge it with this one. Yeah, I can probably do that. Merge with the layer below, and then this one and this one. Okay, and what is this one? This one we don't really need anymore. I'm going to merge this one with the well, I can't rasterize. Oh, I have to rasterize them. Pain. Okay, so this should be here. This should be here, and this should be here. Guys, I'm just trying to keep a little bit of order in all this mess, just because this is going to go online at some point, and you know, it'd be nice that it looks good and understandable. What is this one here? Oh, I think I want, why is H here? Oh, okay, I'm just gonna create another one, H here, and this is going to go here, exactly. And then what about, I'm just gonna add L here to the mix. Yeah. I'm just gonna add L here to the mix. Okay, this looks better now. I'm going to save this somewhere before I lose it, and I'm going to save this also somewhere before I lose it. This is going to be gem distance, and for example also gem distance here. Okay. All right. Now, what are we doing? We're gonna take all of this, we're gonna duplicate it, and we're gonna draw the same diagram right next to it. So can I take all these layers and, of course I cannot. Can I just duplicate this somehow? Layer color. Am I gonna have to merge them? Oh my god, this is so dumb. Okay. Am I gonna have to do this one by one? Okay, what are these options? Duplicate, add layer, delete, rename, edit, rasterize, lock layer. I'm sorry you guys have to go through this, but I'm sorry that I have to go through this too. Should I just rasterize everything? All right. I don't like doing that, but whatever. Okay, rasterize, rasterize, rasterize. And why was I rasterizing? Just because I wanted to. Okay, let's duplicate this layer first. Duplicate the layer, and then how do I move can I move the layer? No. All right. here, let's duplicate this layer, and also okay, here, and I'm just gonna do okay, and then I'm just gonna do a new B. It's going to be here. A is going to be here, and P is going to be here, and H. I want H. All right. Okay, I like that, and then I'm going to turn all of these off because I want to now draw here on this end. Oh, I didn't move this? I did not move this. Okay. All right, more or less. Okay. Oh, and H. Yes, I need to move H back here. Okay. All right, so I think we're back to drawing mode, right? Yes. Okay. All right. So I think we're ready to go. Now I'm going to explain how to do this from a cross product approach. Okay. I'm going to draw in here, and I'm going to create a new layer here. Okay. Okay, so let's do this. All right, great. So I have created a new diagram because what I would like to explain now is an alternative method to computing this distance h. And instead of doing so much trigonometry now, what I'm going to do is I'm going to use one of the nicest properties of the cross product, which is the fact that the cross product equals, the length of the cross product equals the area of the parallelogram formed by two vectors. Let me explain what that means. So if you remember, the cross product is the multiplication of two vectors, but as opposed to the dot product, which gives you a scalar, it gives you a number, the result of the cross product gives you the result of the cross product of two vectors gives you another vector, which happens to be, one of the first properties is that it's perpendicular to the plane that those two vectors form. So those two vectors always form a plane, so the cross product is perpendicular to that plane and with the orientation defined by the right-hand rule. So if I multiply AB cross AP, then you guys no, this is mirrored. This is, sorry, the camera. This is mirrored, but it will be pointing in this way. So this would be the right-hand orientation of this cross product. All right, but most interestingly, what happens is that the length of this vector, the length of the cross product, is equal, and I'm going to make another diagram next to it, is equal to the following. So if we have these two vectors here, those two vectors in the plane that they form a parallelogram like this. And it just so happens that the length of the cross product equals the area of this parallelogram formed by the two vectors. And why is that interesting? It is interesting because we can also use the formula of how to calculate the area of a parallelogram to then find the height. Let me show you that. So if you remember, and you can Google this, the area of a parallelogram equals the base of that parallelogram times the height of that parallelogram. The base would be this one, so it would be B, and the height would be this one here, which, as you can see, this is exactly H is exactly what if I draw this parallelogram here, you can see that that H is exactly the value that we're trying to find, right? Which means that here the value of H equals the area of that parallelogram divided by the base of the parallelogram. And guess what? If we transform this A and this B in vector parameters, what just happens is that what we get is that B, the length of the base, equals the length of the vector AB that we have here. So the length of the vector AB, right? And what is area? Area is equal to the length, as we just described, is the length of the dot product. So it's equal to the length of the vector AB cross product. It's usually used this cross product the vector AP, the length of that cross product. And literally, that's just it. So let me rewrite this in a way that it looks a little bit better for the sake of the diagram. Give me a second. Okay, so wish me luck. Okay, so height is going to be equal to AB cross AP. So the length of that, is it better if I do this? Yes. Divided by the length of vector AB. Okay, and let me clear this up a little bit. So where was I drawing? No, I was drawing here, right? Okay. So let me just I hate doing this, but can I just whatever. I should be more careful drawing with adding layers when I draw stuff. Yeah. And then if I turn on all these things, I can turn them on in a second. Exactly. And this is what I wanted. This is what I wanted to get to. So as you can see now, finding the value of h, that distance, is just as easy as computing the cross product of vector AB and AP. And remember that the order is important in this one. Computing the length of that resulting vector. So those are the two vertical bars that you can see there. And then divide the value of that length, which is the area of the parallelogram, by the length of the base of that parallelogram, which is literally is just the length of the vector AB, which is that's what we're representing with those two vertical bars. All right. So I mean, how easy is this then? Let's now Let's now go back to the code and then to implement this. So I'm going to do it right away now, just because I want to be clean. I'm just going to do this right away on a function. So I'm going to write a function here called this to line, but now it's going to be cross product. And I'm going to take the exact same inputs. Then I'm going to calculate vector AB. I'm going to remember copy pasting is the devil, okay? You've seen me have a lot of problems before doing this, but so be super careful whenever you copy paste code, okay? And now we have the vector AB, we have the vector AP. We can calculate the cross product. So vector 3D cross product equals, and we can use, for example, the static function in Rhino Common. For example, A, B, and AP. And if you guys are interested in how to actually perform the cross product, there's a lot of documentation out there. I can point to some videos here on somewhere. Otherwise, maybe we can actually do this. If we have like a few minutes, we can extend this and just do this manually. That might be a good idea. And then I have the cross product. I have so for example, I can calculate the length of the cross product is going to be equal to cross dot length, just as simple as that. And then what else? If you remember I have to calculate the length of AB. So let's do that. Double A length length AB. I'm just being very verbose and writing a lot of variables and stepwise so that you guys can see. But this could be written in like one line of code. It's just not so easy to read. And I like code that is easy to read and understand, even if it's not so performative, at least for education. And then now that we have both lengths, then the height is just as easy as dividing the length of the cross product by the length of the other vector. So double H equals the length of the cross product divided by the length of AB. And let's return this. Let me see if this works. First, are there any errors? Nope, I didn't have any errors or typos. And then what I'm going to do is I'm going to reshape these outputs, and then this is going to be distance by the dot product, and the other one is going to be distance by the cross product. I'm going to plug them both in here, and d dot is going to be equal to the function that we used before, but now d cross is going to be equal to this two line, but cross product, and then P, the point P, point A, and point B. And let's see, da-da-da-da-da-da, boom, it works. Oh yeah, I love vector algebra. It's one of the coolest things in the world. All right, let me recap. I'm gonna go back to the diagram. So what we just saw here is, I'm going to turn on both diagrams. What we just saw here is two different approaches to calculating this height here. So I'm going to close this. Two different approaches to calculating the distance h between a point and two lines AB. And a line and between the distance h between a point P and the line formed by 2 points A and B. In one, we were using the properties of the dot product and a little bit of trigonometry. And then on the other one, we were using the properties of the cross product of two vectors and literally not trigonometry whatsoever. So from a performance standpoint, they're both very similar, I think. So it doesn't really matter which one you use too much, unless you're doing this like a million times. So just choose whichever you find more useful, more easy to understand, or more practical to implement in whichever framework you're using, okay? And I think with that, I may want to wrap it up. No, what I'm going to do is like bonus points. I'm going to actually write two functions to calculate the dot product and the cross product of two vectors, just for the sake of it, just because I like this a lot, okay? But if you're not interested, if you know how to do that, then this is the end of the video. So see you on the next geometry gem. Okay, and then let's do that. I'm just gonna write. Wait, I never forget. So cross. I always forget the cross product vector. Because okay, vector cross product. And we're gonna do Wikipedia and this one here. This is what I want. Okay. Yay, let's get to this. Let's do first, I'm going to do the cross product. The dot product. Dot product between two vectors. So vector 3, I'm going to call this U, and vector 3D.v, and if you remember, the dot product first is a number, so we're going to return a double, and second, it's very easy to compute. So actually double dot is going to be equal to the sum of the multiplication of the components of each one of the vectors. So this would be u dot x times v dot x, then plus u dot y times v dot y plus u dot z times v dot z. And we just return that. And actually, if we want to really shortcut this, we can just return that value right away. Okay? So let's see if this works. Let's substitute this function with whatever we have used the dot product first. So the dot product here. So the dot product of AP and AB. And then have we used that anywhere else? No. So I'm going to run this, and yes, the result is the same. So yep, pat in the back. I know my dot products. The one that I never remember and the formulation for is the cross product, so I had to look it up. But you can see here the dot product is the result of, is the determinant of multiplying two vectors by an ijk unit vector. So, but you can see here that the first scalar component of the vector is the second scalar component by the third minus the third and second. So let me just put this here on the side. I cannot have. So I'm just gonna put it here on my other monitor here. So first, remember the result of the cross product is a vector object. So I'm going to create a function that returns a vector 3D, and I'm going to call this cross product. And this is going to take two vectors and its inputs. So here, so I'm going to calculate first the x coordinate, and this, as I said, this is going to be equal to y of the first vector times z of the second vector minus z of the first vector times y of the second vector. So let me write that down here. So that's going to be u dot y times v dot z minus u dot z times v dot y. It's very important that you do this super carefully, because if you mess this up, and it's very easy to confuse z, y, v, blah, blah, blah. If you mess this up, it's really hard to debug and find. So I'm going to be super, super careful by doing this. So y is going to be equal to u times z times v dot x, right? Yes. Minus u dot x times v dot z. And you can see that there's like a little bit of like a logic here of how things flip, right? This is lowercase, and then double z is going to be equal to u dot, probably is going to be x, right? U dot x times v dot y minus u dot y times v dot x. And I also got a typo here, u, and then I can just return a new vector 3D that has these components that I just calculated. Okay, this doesn't give me any error, and I'm going to now substitute this where I have cross products. So here with my function, my own cross product implementation, and if I multiply this, there you go. And actually, I just noticed that I have like a huge confusing thing. This is not the cross product, this is the dot product. So that was not great. I'm just going to replace this here. I'm sorry, I made that, that was confusing, okay? That should not have been there. But I think that's it. So with this, now we have our function that calculates both the distance using the dot product and the cross product. And we also have like a bunch of utility functions that give us like a lot of goodness. So I think with this, we're ready to go. With this geometry gem, I hope you liked it. I hope you learned some trigonometry and some vector algebra. This is so cool. And just a reminder, I wanted to build these two gems today because I would like to use this functionality, calculating the distance of a point to a line, to a straight segment line, for a next gem that I'm going to record in a second, which is going to be the Douglas-Peucker polyline simplification algorithm, which uses this. Okay, so if you're interested in that, I will probably have like a link to that video popping up somewhere here, or just like go through the description and you will find that. Okay, well, thanks a lot for sticking around. Good. All right, so we got that. So now let me record the introduction, and we're probably good to take a lunch break, and then we can come back at 3 p.m. Boston time, and then do the polyline simplification algorithm. Remember, for those of you who might be new, remember that this afternoon's stream is going to be on the parametric channel, on the parametric chem channel. We're going to slowly transition. So I just posted the link. Oh no, that was not the link. This is the correct link. This is the link to the parametric chem channel, and I'm going to post here the link to the video, the stream that we will do this afternoon. Okay, it's going to be super intense and super cool this afternoon, so I really want you to join. Let me go back here and let me record the introduction. Okay, so okay. I'm going to start. I mean, I always start with the grasshopper definition, so maybe this is a little nicer to start with. Okay, so I'm going to start here, this video. Hi, and welcome to another video where I'm going to be implementing what we are starting to call a geometry gem, which is basically a super simple algorithm to do some kind of geometry analysis or manipulation. Today's video is going to be about calculating the distance between a point and a line. And the interesting thing about this problem is that that point, that distance is that can be thought as a line that is perpendicular to the first line that we're analyzing. And in order to do this, we're going to apply a lot of we're going to learn a lot of vector algebra. So like you can see here, so you can see that what I have here is a point that I can move around in three-dimensional space, and then I have a grasshopper definition that is giving me the distance of that point to that line that I just formed. And what we're going to implement is these two very interesting functions on how to analyze this problem with vector algebra. And what I'm going to do is I'm going to explain how we can think of this problem as, instead of 3 points, so the point that we want to project and the two forming the line, we can think of this problem as two vectors. So the vector that defines the line and the vector that defines the starting point and the point that we want to analyze, and how through some vector algebra we can find the distance between the straight distance between P and the line formed between A and B. We're going to do this in two different ways. First, the one that you see here, which is we're going to apply a little bit of trigonometry, and we're going to use the properties of the dot product of two vectors. And then the other one that you're seeing on the other corner, which is going to not use trigonometry at all, but take advantage of a really, really cool property of the cross product of two vectors. Okay, so if you're interested in this, follow me and let's get coding. All right. Okay, so I think that's it for this morning. So I will, yes, I'm going to stop here. I have to get lunch and I have student meetings this afternoon. If you guys are interested in joining for the polyline simplification algorithm, feel free to join this afternoon. And remember, we're going to be switching from this channel, my personal channel, Garcia del Castillo. This afternoon, we're going to be streaming from the parametric chem channel. Okay. If I don't show up online right away, it's because I'm trying to figure out how the different connections and the different parameters. We should start streaming around 3 p.m. 3 p.m. my time, Boston time. So feel free to go. Feel free to go to this link here. That's going to be the stream for this afternoon, and subscribe and set a reminder and whatever you need. Okay. Okay. Thank you very much for sticking around, and I'll see you in a bit.